All right, so after seeing a few of those kind of examples of using a pretty inefficient way of going about computing this greatest common divisor, we're about due for actually coming up with a somewhat more efficient way for computing this thing. So as I mentioned, those first couple of examples are in a sense overkill. That first example, we actually had to go about trying to find out all of the possible divisors for both numbers and then go through those lists trying to find the kind of largest one that happened to be in both lists. So that's a lot of extra information that I don't necessarily need when all I'm trying to compute is the greatest common divisor. In a sense, I'm obtaining way more information than I actually need. Likewise, that second example is very similar. The idea is that I was given these two numbers, in this case 60 and 42. I tried to come up with this overall gigantic prime factorization, and from that prime factorization I could actually dive into those little factors and try to determine kind of what this overall greatest common divisor is going to be. Again, that's a lot of extra information. It's a lot of work to actually come up with this prime factorization when all I'm trying to do is just simply compute this greatest common divisor. So in that case, both of those systems are great on their own because they give us lots of information, but it's in a sense too much information when all I'm trying to do is compute the greatest common divisor. So in this case, I want to slowly move towards a way of actually computing something that's going to be a little bit more efficient. So the algorithm that we're going to be presenting here is often referred to as the Euclidean algorithm. Though you should be aware that some texts actually refer to this thing as Euclid's algorithm, and they're saying the exact same thing in this case. It just depends on which kind of version of this thing do you want to look at. Do you want to call it the Euclidean algorithm, or do you want to call it Euclid's algorithm? They're saying the exact same thing. So in this case, I learned it as the Euclidean algorithm, so that's how I'm going to reference it. But for those of you that are maybe using other resources or the internet or something like that, just be aware that you might see this referred to as Euclid's. So the idea in this situation is actually pretty simple. What we're going to be doing is actually taking this kind of question of trying to find the GCD between 60 and 42. In this case, I'm going to use 60 and 42 because we've actually seen this GCD a few times, so we know the answer is supposed to kick out a 6. So whatever process I'm going to have in this case better kick out a 6 at the end. So the idea is that I'm going to be given two relatively large numbers. So in this case, these numbers are obviously not very big, but as we go forward, we're going to take these things and they're going to become much larger. And what I want to do is I want to slowly chip this thing away to make this a slightly easier problem. And the way that I'm going to do that is I'm going to replace these 60s and 42s with slightly smaller numbers. And the way that I'm going to bring about these smaller numbers is through division. So it's going to be this nice little process where we're going to start with a number, we're going to run this division algorithm, and we're going to get a new pair of numbers. And then we're going to run that process one more time, and then another time, all the way until we get to a nice little stopping point. So for those of you that are interested in the coding world, you're going to see a really nice little algorithm or a process come through this. You're going to see kind of the natural line of code that's going to occur. You're just going to have this one single little loop that's going to run a whole bunch of times, and then at the very end there's going to be this return statement which says, okay, go ahead and return this GCD now. So the idea in this case is that, like I said, we're going to start with this pair of 60 and 42. What I'm going to do in this situation is I'm going to run this division algorithm on this thing. So I'm going to take 60 and I'm going to divide it by 42 and try to think about what that remainder is going to be. So in this case, I'm going to have 60, and I know that 42 is going to go into 60 one time, and I'm going to be left with a remainder of 18. So in this case, I know that 60 modulo 42 is simply going to kick out an 18. So in this case, I'm going to now take this stage and I'm going to create a new pair. So the pair that I'm going to be looking at is going to be that 42 that I started with, and now I'm going to take that second number to be an 18. So my new pair is going to be that initial divisor, and then now I'm going to be dealing with my remainder. So here's my little d, and this is now going to be my r. And that new pair is going to be connected to my original pair, and that special property that's going to be obtained between these two things is that they're going to share the exact same GCD. So what's going to happen is that I'm going to go from this large pair of numbers to a smaller pair of numbers, and then slowly trying to chip away to start to see something that's going to be a little bit easier to work with. So now I'm just going to run this process one more time. So I'm going to take this 42 and that 18, and I'm going to run this division algorithm on this thing. So I'm going to look at 42, and I'm going to try to think about how many times does 18 go into 42. So in this case, I know that 18 is going to go into 42, in this case 2 times, and I'm actually going to be left with a remainder of, in this case, a 6. Because if I take that 18 times that 2, I'm going to be up to a 36, and then I'm going to be short by 6. So in this case, I'm going to have a remainder of 6. So now I'm again going to look at, well, here is my initial divisor, here's my new remainder, and that's going to become my new pair. So I'm going to have the 18 and the 6. And again, I'm down to a slightly smaller grouping of numbers to look at. So I initially started with 42 and 18. Now I'm down to an 18 and a 6, and I'm going to run this process one more time. So I'm going to now start with this new pair of 18 and 6. I'm going to run the division algorithm on this pair, which is going to give me an 18. And in this case, I actually know that 6 goes into 18 very nicely. In this case, it's going to go in 3 times, and I'm going to be left with a remainder of 0. So in this case, my last little new pair is going to be that 6, and now I'm going to have that remainder of a 0. And that's actually going to be my stopping point. I'm going to run this process all the way until I get to a stage that I have a remainder of 0. And what's going to happen is that now I'm going to have information about what my GCD is. I'm now down to the stage of looking at this pair 6 and 0. So if I was given these two numbers, 6 and 0, and I was asked, what is the greatest common divisor of these things? Well, I'm not really going to care about that 0 because I know everything goes into 0 very nicely, so I'm left with just the 6. So the question is, what is the largest number that goes into a 6? And the answer in that case is simply a 6. So what we end up having is we have that the GCD of this ordered pair 60, 42 is actually going to be equal to the GCD of that last little pair 6, 0. And that's actually going to come in the next theorem. I'm going to kind of give you the big overall theorem statement. I'll actually show you the overall proof. I'm not going to dive too far into that. I really care more so about if you understand this process of actually doing this division algorithm over and over and over again, trying to work down to the stage of actually having a 0 remainder, and then I'm going to go back to the number that I had before that 0 occurred. So in this case, it was a 6. So what ends up happening is that this GCD of 60, 42 is equal to the GCD of 6 and 0, which in this case, this is going to equal a 6, which is nice because that's exactly what we were expecting to see in this situation. So the slightly more kind of formal version of this, and this is what I actually have in the filled out notes, is actually tracing this little 6 that you see through this entire process. So after I do this division algorithm a couple times, I got down to the stage that I had this pair 18, 6. And at this stage, I know that the GCD of 18 and 6 is going to be a 6 because 6 very nicely goes into that 18. So in this case, that's why I end up seeing that remainder of 0. So in this case, what ends up happening is that I can chug through this whole process back up to my beginning pair that I was looking at, which is this 60, 42, and I know that it's going to have a GCD of 6. So what's nice about this is that every pair of numbers that you see in this column over here, all of those numbers are actually going to have the exact same greatest common divisor, which in this case is going to be that little 6. So the reason for this, and this is exactly kind of the guts that makes this Euclidean algorithm work, is actually knowledge about this quotient or this kind of division algorithm statement that comes into play. This idea that if you have something that looks like A equals BQ plus R, which is exactly what we have in the middle step of all of these division algorithms, if you have that occur, then the greatest common divisor of the A and the B are going to be the exact same thing as the B and the R. So I can kind of shift my focus from my initial pair AB and move it to this pair BR. And that's what's happening in this case. I initially start with 60 and 42, and then I'm going to look at the 42 and the 18. Likewise, the 42 and the 18 is then going to suck into the 18 and 6. So that's the idea in this process, is that I'm going to continually bring about smaller little pairs up until the stage that I have a pair that's really easy to work with. So in this case, the pair 6, 0, I immediately know that the greatest common divisor there is going to be a 6, and I just run that thing all the way back and say, okay, the initial pair that I was working with has a GCD of 6. If you're interested in seeing the kind of overall proof of this thing, I do have a sketched out version of it. It's actually pretty nice. It's the idea that if you have one of these statements, I'm going to really be looking at this idea of what divides what, and then it's really the kind of question of if these things share some divisors, I know that they must have the same greatest common divisor. So if you're interested in kind of taking a really quick read through that thing, I'm not going to make you reprove something like this, but it is nice to kind of see all of those little pieces come into play. And if you're really adventurous, you can actually see the big overall Euclidean algorithm, kind of the book definition of what's happening. So the natural question is, as you're doing one of these things, the question is this process ever going to stop? And that's always should be a question when you're working in some of these algorithms, is it potentially going to be the situation that I'm going to kind of go down this rabbit hole and my computer is going to run forever because it's never going to claw itself out of this little hole? But the idea in all of this is actually embedded in this division algorithm. So if you remember this idea of if I'm given numbers A and B, if I actually go ahead and do this division, what's going to happen is that that remainder that's going to be kicked out is actually going to be smaller than the thing that you divided by. So if you go back to the example that we were looking at, I ended up starting with a 60 divided by a 42, and I get a remainder that's smaller than that 42. I have to get a remainder that's smaller. If this was a 43, this means that I didn't divide by enough stuff, or I didn't pull enough stuff out of it. So every step that I go, I'm going to continually get smaller and smaller remainders. So in this case, I'm going to start with some number, and then I know that as I get smaller and smaller, at some point in time, it's going to have to go to a 0. And once I hit that 0, that's going to tell me that my process is done, and I can kick that last non-zero remainder out as being my GCD. So that's exactly what the process is you do this division algorithm as many times as you need up until the stage that you actually get a 0 remainder, and once you have that 0 remainder, you kick back that last non-zero thing, and that becomes your GCD. So like I said, if you're interested in seeing the full guts of what makes this true, you can take a peek at this giant slide. It's a little bit easier just to go through a bunch of examples to start to see kind of what's going on. So that's exactly what I'm going to do here. I'm going to start with two slightly larger numbers. So in this case, I'm going to look at the numbers 1,000 and 5,040, and I'm going to try to compute the GCD of these things using this Euclidean algorithm. So what I want to do is I want to start with my initial pair of 50, 40, and 1,000. What I want to do is I always want to put that larger number first because it's going to make that division algorithm step a little bit nicer. So now the question is going to be, how many times does 1,000 go into 5,040? So in this case, hopefully you can see that it's going to go in there 5 times because 5 times 1,000 is 5,000. So I end up with 50, 40 is going to be a 5 times 1,000 plus that extra little remainder of a 40. So in this case, this 1,000 and that 40, that's going to become my new pair. So like I said, we're always chipping away at this idea. I'm going to start with this divisor of 1,000, and now I'm down to a divisor of 40. So that's exactly what's happening in this giant process, is that all of these little divisors and then the little remainders that are going to occur are going to continually get smaller and smaller, ultimately going down towards 0, and that's going to be my stopping point. So now I start this thing up again. I'm going to look at 1,000, and I'm going to look at 40, and I'm going to try to see how does this thing divide. And what's nice about this is you can see that it stops relatively quickly. I'm going to have that 1,000. Well, I know that 1,000 and 40 are going to play relatively nicely because 40 actually goes into 1,000, and it's going to go into 1,000 25 times. So in this case, I'm going to have that, and I have this little remainder of a 0. So my new pair is going to be this 40 and 0, and I see that 0, so it's going to tell me, hey, I'm going to stop now, and then my last non-zero remainder is that 40. So that tells me that my greatest common divisor of those two things is not question marks anymore, but it's going to be a 40. So like I said, it's a pretty quick thing. Once you actually kind of start to see this process take shape a little bit, it becomes not such a horrible thing to see. So we're going to go ahead and dive into another example. So here's my double check to make sure I did it correctly. So we're going to go ahead and dive into another example. So in this case, I'm going to be looking at the greatest common divisor of 330 and 228. So like I mentioned before, I'm going to start with the larger of the two numbers. So in this case, 330 and a 228. I'm going to try to run this algorithm on this thing. So I'm going to see how many times does 228 go into 330. In this case, it's going to go in once, and I'm going to be left in this case with 330 minus 228. I'm going to be left with a remainder of 102. So what's going to happen is that those two things are going to become my new pair. So I'm going to have a 228 and a 102, and I'm going to bring those over here. So 228 and a 102. So like I said, you can see that I start with this 228. It's now being chipped down to a 102, and I'm ultimately hoping to see a 0 pop out. So now I'm going to look at 228, and I want to think about how many times does 102 go into that. And I know that 102 is going to go into that thing twice, because 2 times 102 is 204. So 2 times a 102 is going to be a 204, which is going to say that I'm going to have a 24 left over. So now I'm going to take this 102 and that 24, and I'm going to run this process one more time. So I'm going to start with a 102, and I'm going to have a 24, and I'm going to do this again. So how many times does 24 go into 102? You're going to see that 24 is going to go into 102, what did it look like, 4 times, because a 102 is going to be a 4 times the 24, which is going to bring me up to a 96 because it's 4 less than 100. And then you're going to see that I'm 2 over, so in this case I'm going to have a remainder of a 6. So my new pair is going to be the 24 and the 6, so a 24 and a 6. And I run this process one more time. So I'm going to have a 24, I'm going to have a 6, and now you can see I'm going to stop after this stage because 6 is going to go into 24 very nicely because I know that 24 is 4 times 6, and I have a remainder of 0 here. So in this case, I'm going to have this new pair of 6 and a 0. So here's my 0. So that's going to say that all of these things over here are all going to have the exact same greatest common divisor, and that greatest common divisor is going to be this very special number that was the last non-zero thing. So in this case, it's going to have a GCD of 6. So like I said, it looks kind of scary when you first start doing these things because it's a lot of little processes that you're kind of having to grind through a bunch of these computations. But what's nice about this is that all you really care about is this little remainder. You can kind of see this 102, this 24, this 6. So if you're good with this kind of modular arithmetic step, you know that that little process is simply going to be whatever 102 is modulo 24 is going to kick out a 6. This is 228 modulo 102 is going to kick out a 24, and likewise. So in terms of coding this thing, all you have to do is keep track of what this little remainder is, or this modulus, as you kind of go through this gigantic process. So it's not so bad. It's kind of worse actually from the handwriting side of things, but once you've actually seen a few of these, you can code it with some really bad pairs of numbers and start to see some really bad stuff occur. So I'm probably going to give you that as one of these little activities for those of you that are really interested in the coding side to kind of see if you can actually go ahead and code one of these Euclidean algorithms, and then I'll actually go ahead and give you the code for this thing as well so you can actually compute some of these gigantic messes of things rather than having to do these things by hand over and over and over again. Because you very quickly could be given an example. For example, look at the GCD of 3,454 with 4,666, and you're going to see that this takes a lot of steps. There's a lot of little things you can mess up as you go. There's a lot of little divisions that are going to occur that don't become so fun to do by hand, but a computer is super good at computing things like that, so you might as well kind of go let your computer grind through a bunch of those computations, and then at the end you say, oh, there's the last non-zero thing. So the greatest common divisor between those two things must be a 0. So like I said, you're going to see a few extra examples of those, just kind of trying to practice kind of going through this Euclidean algorithm. It does seem really scary when you first start doing it, but after you do a couple examples, students usually get the hang of it pretty quickly. It takes a little bit of time because you're just kind of having to grind these things out, but it's not such a terrible thing to work with.